In this lecture, we're going to talk about input data normalization. Why input data normalization? So input can be given in different formats. Maybe someone gives you an image in the range of 0 to 255. Someone else has an image in the range from 0 to 1. Also, different features can naturally have different scales. Maybe we have features describing a human, and then the age might be in the range from 0 to 150, and the height might be in the range of 0 to 3 meters. Also, some people argue that having the data zero-centered, that means that the data points are distributed around the 0 point, may help improve the training. To make this lecture self-contained, we're going to review the data matrix, a rank 2 tensor. And we're going to start explaining normalization just using the assumption that data is given as a matrix, and later we will extend to higher order tensors such as images. The data matrix storing the data stores n samples. So each sample is one input, for example, one image is one sample. And so we have n of these samples, and the dimension of the sample refers to the different variables or features describing a sample. So for example, we would say that an image has d dimensions, and each dimension corresponds to a pixel, or if they're RGB color channel, then each dimension would correspond to one of the color channels within one of the pixels. So let's look at this data matrix below. So we say this data matrix X has as many rows as we have samples, or as many rows as we have images, for example, and then within each row we do have one sample. For example, the first image will be stretched across the first row, as here. The important thing to note now for the following slides and for the notation is that here when we write X subscript I, this does not refer to the ith component of a vector. This refers to the ith sample in the data set, the ith row in the data matrix. So X subscript 7 is the 7th image in the data set. All right. So again, let's say the image has is grayscale and has 1,000 different pixels, then we would have 1,000 different columns here. Also, to make it self-contained, just some examples again, but just the only thing to mention here now is that we're going to start with vectorized samples first and see how everything looks like when we have vectors as input to a network. Also, the general disclaimer, we ignore all technicalities such as biased and unbiased estimators or known and unknown distributions. We're just going to look at everything from a pure calculation standpoint. First, we need to compute some statistics of the training data that is then used for the normalization. For basic normalization, we are computing the sample mean and variance, and for advanced normalization, that's typically not used in deep learning, we would also compute the covariance or correlation. So when looking at the equation, the most important thing to remember is that we are computing one scalar value, one mean value per column of the data matrix. So we are obtaining the different scalars, the different mean values, one per column. So here x subscript 1 does not refer to the first sample. We're just looking at something different now. This refers to the first mean value across the complete data set for the first feature dimension. Also from the equation, it might seem we're computing something per row. Also, if you look at the equation, that just means we list here how is each of these values computed. This is a column vector that actually contains the means that we described, but each of these equations here refers to one column of the data matrix, not to one row. So how is this how are these values computed? Let's go back to the data matrix slide. We would compute the mean across the first column going down here. So that's what this equation says. And that means we need to touch the complete training data set in order to compute this mean vector. The joint variability of any two variables, two features, two dimensions, or two columns of the data matrix is given by the sample covariance matrix. Again, important is to look at the dimension. The dimension is d times d. So if we have images, that would be number of pixels times number of pixels. The covariance matrix, the size, is independent of how many samples are in the data set, independent of how many images there are. For example, we'll give the equation for completeness, and you see this is a sum where we sum over some expression where we have one term in the sum per sample in the data set, and this is the well-known equation for covariance. And we have one such value for each pair of dimensions. So note that when we compute C of something where P equals Q, so C 7, 7, then this is the variance of the seventh dimension, for example. That means if we put all these covariances into a matrix, let's look at this matrix down here, then again we see the matrix has dimension d times d, and so CD1 is the covariance considering dimension d, the last dimension, and the first dimension. This matrix is going to be symmetric, so this element here, CD1, is going to be the same as C1d, and the variances are going to be on the diagonal C11 to CDD. Therefore, the vector of standard deviations can be computed from the diagonal of this matrix C by taking the square roots of the diagonal elements. Now we're going to review multiple possible ways to normalize. We're going to consider samples xi with a sample mean x bar and a sample standard deviation s. Note that x bar and s are vectors and they both have d components. And xi is the ith sample. Again, this is not referring to the ith dimension. So xi is a vector in R to the power of n. So when looking at the first normalization, C-score normalization, again, it's important to consider that these are vector variables. So xi is the ith sample that has d dimensions minus the sample mean, which is a vector of d dimensions. So as output here, we get another vector of d dimensions. And the process of subtracting out the mean is going to zero center the data. Wherever the data started out with, if you imagine some higher dimensional visualization, after performing this subtraction, you would expect that the data is kind of centered around the 0 point. And now we divide by S, but it's important to note that this is a component-wise division. We're dividing a vector that has d components by another vector that has d components. As output, after all the data is normalized, we would expect that most values are between -1 and 1, but the minimum and maximum can vary depending on the input and is generally not bounded. For something like images, it might be possible to compute some bound, but in general, you have to carefully determine the bound. There's not like an obvious bound that comes out of this equation. So if they're outliers, they can have values that are much larger or much smaller in their absolute value than 1. Here's some Python code. If we have some data matrix, I just create some random data matrix, then to compute the mean per column, then we say we want to have the mean, and then here we give the axis of the tensor. So this is axis 0, gives you 1 mean value per column, and then we can also compute the standard deviation with one command, and then Python gives us this nice vector arithmetic, so we can compute the normalized data matrix by computing x minus mean divided by the standard deviation. Again, this is an equation that has x as a matrix, and this is a vector mean, so we're going to use some broadcasting divided by standard deviation, and this is going to work out well. Here's some inspirational visualization of what's going to happen to the data. We see the original data in red, and we would estimate that the center of the data is somewhere around here. So after subtracting out the mean, we obtain this data that is zero-centered. And in this visualization, we have many samples, each sample represented by a point, but there are only 2 dimensions. So each sample has only 2 different features. So you could imagine this being an image data set where each image is only described by 2 pixels. After dividing by the standard deviation, we obtain this normalized data that would come out if we apply the equations discussed in the previous slide. This minimum-maximum normalization does not subtract out the mean, but the minimum, so the x-min is a d-dimensional vector of minima per column, and then we divide by x-max minus x-min. That is also going to be computed per column, so we kind of have the range per column. And as output here, we would have all values normalized to be in the range from 0 to 1. A general version of min-max normalization does not only normalize everything between 0 and 1, but it will put it in a range between AI, BI, and this is the equation to do it. Maximum absolute value normalization divides by the absolute value, the maximum absolute value in each feature dimension. So that means that after dividing like this, the absolute values of the output are mapped in the range 0 to 1. But we don't know if the absolute value is determined by the negative or the positive samples. So it could be, for example, in the 7th feature dimension, the largest value in absolute value has been a negative sample. So then if there's a negative sample that's, let's say, minus 1,000 and the largest positive one is only 100, then the value afterwards, in absolute value, it will be a -1, but the data will not reach like +1 in that feature dimension. So in each feature dimension, the data is between -1 and 1, but depending on how the data was before, either there will be a -1 or there will be a +1. And only if by some strange coincidence the largest in absolute value, negative and positive value have been the same, then there will be a -1 and a +1 in that feature dimension. In robust normalization, we would like to make the normalization procedure less sensitive to outliers. One general idea is to replace the mean with the median. So what we see here, instead of subtracting out the sample mean, we're subtracting out the median, where x subscript 0.5 refers to the median computed per feature dimension, so it's a d-dimensional vector. More general, we then also use quantiles, so x subscript q something refers to some quantile, and what we use here is are two quantiles. For example, this could be the 25 and 75 percentile here. So we divide by the span between whatever these quantile numbers are. And that makes us eliminate also by this, in this division, we don't use the full range between minimum and maximum, which is sensitive to outliers, but we try to eliminate, if we use these particular values, maybe the bottom and top 25%, maybe these could be outliers. In praxis, maybe you have a lot fewer outliers, so you might use something like 0.1 or 0.9. It really depends on the data. After this normalization, we do not know the feature range. It will be dependent on how big the outliers are. However, for most of the data, we will normalize it in a small range. That is not even between -1 and +1. It's going to be a smaller range than that. Let's move now to the practical case of normalizing input images. We assume we have images of the form width times height times 3. The first idea is we really compute a mean image of size width times height times 3, estimating the sample mean, and subtract it from each image. We don't do anything with the standard deviation. We just subtract out the sample mean because we say, well, the images, assuming they have been in the range 0 to 1 before, they don't really spread out unpredictably, and with the simple data formats, there isn't any possibility for outliers anyways. Also, we can just compute the mean pixel color, so we only have some sort of a pixel color mean that is a three-dimensional vector, and subtract it from each pixel. Or we can perform full z-score normalization per pixel, where we are computing a mean vector with 3 dimensions for the pixels and a standard deviation vector for the pixels. So a corresponding Python command looks like this, where you normalize, you say this is the mean, and this is the standard deviation. So if you look at this, then what you see is that the mean is not 0.5, 0.5, 0.5, what you might expect, but the mean is a bit darker than that. So you could say that maybe in some sense the average image is darker than what you would expect. And also you see that the values across red, green, and blue are not the same. So red values tend to be higher than green values, which tend to be higher than blue values. But still, basically everything is possible. You could also normalize to 0, 1. You could compute the complete mean and standard deviation image and normalize using that. Or you could think about normalizing maybe to 0, 1 and introduce a trainable normalization layer as the first layer of your network. So for now, let's just say you use something like this, the idea 3. That's maybe what I would start with. Other crazy things, you can go and experiment with. And the other general advice is start with an existing state-of-the-art network and just do whatever this existing state-of-the-art network does. Again, things are heuristic, so it's difficult to give general advice, and the input data normalization interacts with all other normalization in the network and with all other components of the network architecture. For example, the batch normalization. Any pre-processing statistics, for example the data mean, must only be computed on the training data set. If you're computing also on the test data set or validation data set, you're making a mistake. It is basically using information from, for example, test data, which is illegal in machine learning. The values estimated from the training data can then be applied to the validation and the test data. So you do have to normalize, of course, the input, validation, and test data. You're just not allowed to use this data to compute statistics. So the first mistake then would be to really compute the statistics on all the training, testing, and validation data. Another mistake would then be to only normalize the training data but leave the test data unnormalized. And another mistake would be to use different normalization as was used during training. So you are downloading a pre-trained network, and then you have the great idea to change the normalization to try out something else that is not going to work. Also, we briefly want to mention advanced normalization. Advanced normalization is, for example, using PCA. So now we're not going to go into details of this. There's a set of loosely related techniques like PCA, eigenvalue, eigenvector decomposition. So let's just say we have the covariance matrix as described before. Then we can use a standard linear algebra package to compute an eigenvalue, eigenvector decomposition. So if you look at this data set, then what we would expect is we would want to get the vectors, the eigenvectors, pointing along the major modes, the major variations in the data. So the first major variation would be along this axis here, and then the second variation would be orthogonal, would be along this axis here. And so what we then would do is, again, we need to subtract out the mean. Actually, we need to look at the data after subtracting out the mean anyway. So we want to get the vectors. We want to get these main directions in the zero-centered data. And then we can use these directions to rotate the data cloud to be axis aligned. So what you see here in the green data is that the first eigenvector is aligned with this x-axis and the second eigenvector is aligned with the y-axis. Also, this matrix factorization gives us eigenvalues, and the eigenvalues can be used to whiten the data. So this is called whitening the data. And if you do this additional step, then you would perform something that's, inspirationally looks like a higher dimensional ellipse that can have can be squashed and very thin in some directions, very spread out in others. It would perform it more. It would transform it more to some sort of a uniform distribution. It looks more like a circle than an ellipse. Other ideas would be to use PCA to do some dimension reduction before processing the data. We can just look at some examples here. So there's some original images. These would be the top 144 eigenvectors, where each eigenvector is an image itself we can project basically on this eigenvector basis, so we get some dimension reduction. And so this is what you would get if you would whiten the data. Now, of course, there's always the problem with the visualization, because after whitening the data, you have negative and positive values. So you got to shift back and transform back somehow to actually be able to visualize the data as images. This concludes the lecture on input data normalization.